A warm welcome to Electronic Circuits Lecture 5. In this video we will learn about analysis of CEC amplifier, which is common collector amplifier, or it is also called emitter follower circuit using hybrid pi equivalent circuit. So this is the common collector amplifier. It could be called as emitter follower. Why? Because we are going to give the input to the base and take the output at the emitter. So my emitter is following the base input. That's why it is called emitter follower. That means the input voltage and output voltage tend to be equal, and my voltage gain is nearly equal to 1, and that's why it is also called voltage buffer. That is the reason why common collector amplifier is called voltage buffer and why it is called emitter follower. The emitter terminal is going to follow the base input, that's why it is called as an emitter follower. And we will understand why it is called emitter follower or common collector amplifier. So if you consider AC wise, the collector terminal should be considered should be grounded. If that is the case, if this terminal is being grounded, you consider this. Now the input is with respect to collector terminal and output is taken with respect to collector terminal. That's why AC wise collector is at AC ground. That's why it is called as a common collector amplifier. We will draw the small signal equivalent. This is my Vs and this is my Rs that will be coming because of the source which has been connected to the circuit. The coupling capacitor is considered as short circuit, so there is a short. If you ground this, R1 and R2 will appear to be in parallel. This will come. Between base and emitter I have a resistor which is R pi, which is because of diffusion resistance. Between collector and emitter I should have a current source which is GMV pi, or I could write it as beta times IB. I have taken beta times IB, and R0 is present because of the early effect. In the emitter terminal we have resistor RE, so RE will come into picture, and then we are going to take RE across V0. So what we do is we are going to make this beta into IB parallel with an R0. We are going to tilt it and we are going to draw it in the modified form of this type of diagram. So this is the small signal equivalent of the common collector amplifier, and this is the algorithm we are going to follow. We will understand this in the coming slides. We want I0, so this is I0. So this is the current which is been entering, and this is the current which is been entering. You apply KCL here, apply KCL. It becomes IB plus beta times IB. So take IB as common, 1 plus beta. So this is what is I0. And what is V0? V0 is this current which is going to be circulated here, these two currents. So it is V0 is I0 into R0 parallel RE, I0 into R0 parallel RE, which is I into R. That has been written. What is Vin? Vin is voltage across R1 parallel R2. The whole this is the input impedance. If you consider the input impedance, it will be R1 parallel R2. Again we have this R pi, where if you measure if you take this transistor, if you measure resistance at the base, it is nothing but RIB. If I measure the resistance at the base, we have R by between base and emitter, and we have RE the base and emitter is going to differ by a current which is 1 plus beta. So what will be the thing is, it is R pi, which is between base and emitter, plus the current ratio is going to differ by 1 plus beta times between base and emitter, so it will be 1 plus beta. And here you have R naught, here you have Re, so R naught parallel Re, that will be the resistance measured at the base, right? And this Ri is total impedance at the base, which is R1 parallel R2 parallel Rib. So if you consider this Vin, which is nothing but Ri divided by Ri plus Rs, which is nothing but voltage divider rule. We have applied voltage divider rule and we have obtained this. So what is V naught? V naught is Ib into 1 plus beta into R naught parallel Re. Voltage gain is V naught by Vs. So if you consider this, V naught is this quantity. Instead of Ib, I am going to write Ib is equal to Vin by R pi plus 1 plus beta into R naught parallel Re. So that's why you are getting this term. And Vin is again, it is nothing but this. So you substitute all this, you will end up getting this equation, right? This is the exact gain. If you do an approximation, normally this Rs will be small, so the whole term will become equal to 0, and you will end up getting 1 plus beta R naught parallel Re. So this R pi will be much less than 1 plus beta R naught parallel Re. So you can neglect this. So what is happening is 1 plus beta into R naught parallel Re divided by 1 plus beta R naught parallel Re. This whole term can be cancelled and you will get 1. So voltage gain is 1, which is nothing but, you can call it as voltage buffer. Whatever you give at the input, that will be available at the output. You will not attain any gain. That's why it is called as an voltage buffer. If you want to calculate output resistance, you connect a source which is Vx, connect source Vx and measure Ix. So R naught is Vx divided by Ix. So Vx is the quantity which has been applied and Ix is to be measured here. So that will end up giving R naught. So this is the first step, and second step is you have to make Vi equal to 0. So apply KCL here. So these are the currents which is you have to apply KCL at the emitter terminal. So Ix plus Gm into Vx. These are the currents which is entering, and these are the currents which is leaving. These are the currents which is leaving in this node. So all these have been included, and you will end up getting R naught is equal to R pi divided by 1 plus beta parallel Re parallel R naught. It is same as that of your common base amplifier input impedance. Now this terminal has been considered as an output terminal. So it is equal to R naught is equal to R pi 1 plus beta, and if you make approximation out of these three combinations, this is going to be the smaller value. So the equivalent resistance or equivalent impedance at the output will be R pi by 1 plus beta, which is equal to Re. This is the output impedance of your common collector amplifier, and this 1 by beta is nothing but inverse resistance rule that is coming because of the difference in current between base and emitter, right? And what is the speciality in common collector amplifiers or emitter followers? We will obtain current gain. So current gain is IE by IA. So what is IB is the current flowing through R pi is IB. So if you want to calculate current through R pi, then you should consider R1 parallel R2 divided by R1 parallel R2 plus RIB into total current, which is IA, which is nothing but current division rule. So this has to be applied. I naught is this current, and this is current is IB, and this current is beta times IB. If you add that, you will get 1 plus beta into IB. 1 plus beta into IB. IB is this, so you include this. So I naught is this value. You want IE. AI is IE by II. So if you want to calculate IE is nothing but current flowing through RE. If you want IE, you have to apply current division rule, which is R0 by R0 plus RE, which is multiplied with current I0. So your I0 is this value. You substitute this. You will end up with this equation. And if you make approximation, RE tend to be much smaller compared to R0. So you can neglect this. If you neglect this, this whole term will become equal to 1. This whole term will become equal to 1. And if you consider this, RIB will be much smaller than R1 parallel R2. You can neglect this. So if you neglect this, you will get equal to 1. So finally you will get AI is equal to 1 plus beta, which is the current gain of the common collector amplifier. So it is approximately, you can even approximate this, which is equal to beta. Yes, you will obtain current gain in the case of common collector amplifier, but voltage gain will be nearly equal to, so voltage gain will be nearly equal to 1. Current gain is equal to beta, and R0 is equal to R pi by 1 plus beta, and Ri, which is equal to R1 parallel R2 parallel R pi plus 1 plus beta R0 parallel R. So this is the consolidation of common collector amplifier. And thank you all. Thank you.